Yeah.
He just kind of dropped it.
We're going to finish it by talking about horizontal and vertical tangent lines in parametric curves. Let's remember, generally, tangent lines are horizontal when the slope of the tangent line is 0. And if the slope is 0, that means the derivative must be 0, right? So, the statement here, horizontal, if the derivative of y with respect to x is equal to 0. Well, what does that tell us? And what does that tell us? Remember the way we calculate the derivative of y with respect to x? We calculate it by calculating the derivative of y with respect to the parameter, I'm calling t here, and dividing that by the derivative of x with respect to the parameter. And so if the derivative of y with respect to x is equal to 0, that implies, here we have a fraction that's equal to 0. That implies that the derivative of y with respect to t has got to be 0. The derivative of y with respect to t must be equal to 0. But that fraction won't be 0 if, in fact, the denominator is 0. So we also have to say not only is the derivative of y with respect to t equal to 0, but simultaneously the derivative of x with respect to t is not allowed to be 0. So that's when we have horizontal tangent lines. This condition, or these two conditions, must be true. Now, on the other hand, tangent lines are vertical when the derivative is undefined. Okay, and of course they're vertical when the slope is undefined, aren't they? So, pardon me, the slope calculated by using the derivative, that would be when the derivative is undefined. Well, it's the same kind of argument that we just had. The derivative of y with respect to x, okay, being the derivative of y with respect to t divided by the derivative of x with respect to t, it would be this calculation that it had to be undefined. The way that will be undefined is if the denominator is 0, okay? So that means the derivative of x with respect to t would have to be equal to 0. Now, we can't have the numerator being 0 also, because that would be an indeterminate form. So, along with the denominator, the derivative of x with respect to t being equal to 0, we've got to have the derivative of y with respect to t not being equal to 0. So, these are the, for horizontal, this is the condition that needs to be true, the two conditions. And for vertical tangent lines, these are the two conditions that must be true. I must add here, if both the derivative of y with respect to t and the derivative of x with respect to t are both equal to 0, we can draw no conclusions. Now here's what I mean. We're looking for values of the parameter where derivatives are 0. And if we find a value of the parameter t where both derivatives are 0, then we don't know whether we have a horizontal tangent line there or not, because we would have the derivative of y with respect to x being an indeterminate form. And when we have an indeterminate form, there's no telling what the situation is. So we have to have one 0 and the other not. Well, we'll continue on the next page by looking at a problem, a curve which we will find both horizontal and vertical tangent lines. So we're to find all the points on the graph for which the graph of the parametric curve has horizontal or vertical tangent lines. And the curve is defined by x equal t cubed minus 3t and y equal 3t squared minus 9. Now, before we get started, we know that we're going to need to have the derivatives of both x with respect to t and y with respect to t. So let's just go ahead and calculate those as we get started. The derivative of x with respect to t, of course, is very simply 3t squared minus 3. And the derivative of y with respect to t is very simply 6t. Okay, now for horizontal tangent lines, here's what's necessary. Here's what's necessary. The derivative of y with respect to t must not be equal to 0, but simultaneously the derivative of x with respect to, excuse me, my bad, is equal to 0, and the derivative of x with respect to t is not equal to 0. So we find out where the derivative of y with respect to t is equal to 0. Remember, the derivative of y with respect to t is 6t. So where is that equal to 0? Okay, only when t itself is 0. That's a simple equation to solve. Now the question becomes, is the derivative of x with respect to t evaluated at this t's value equal to 0 or not? Well, we see that it's 3 times 0 squared minus 3, which is not 0. So this is a good t value for having a horizontal tangent line. Now, from that t value, okay, 0, what is our x and what is our y? Well, we would look above and we would calculate our x. We look up here for our definition of x, and we would get an x value of 0. And we would look above when t is 0 to calculate our y, and we would get a y of negative 9. So the point at which we have a horizontal tangent line is the point 0, negative 9. Now, as far as vertical tangent lines go, what do we need? Well, we need the derivative of x with respect to t to be equal to 0, but simultaneously the derivative of y with respect to t not 0. So we set the derivative of x with respect to t equal to 0, and that would be 3t squared minus 3 equals 0. And it doesn't take very much work to decide then the solutions to this equation would be positive and negative 1, plus or minus 1. Well, now the question ends up being, what about the derivative of y with respect to t at either one of those? Okay, at t, and I'm abusing notation a little bit. We can't evaluate at both positive 1 and negative 1, but you see if we evaluate at positive 1, we get a 6. If we evaluate at negative 1, we get a negative 6. So the result here would be either a positive or a negative 6, which is not 0. So both of these t values are valid t values for our calculation. That is, both of those will give us points where we have vertical tangent lines. So in the case of t equal negative 1, we calculate our x value by looking above, and what do we get? Negative 1 plus 3. Negative 1 plus 3, which is a positive 2. And we calculate our y value of being 3 times 1 minus 9, which is negative 6. And so we get the point 2 comma negative 6, we have a vertical tangent line. Now, the t value of 1 will give us an x value of negative 2 again. Of negative 2 this time, pardon me. And our y value will once again be negative 6. And so another point where we have a vertical tangent line is the point -2, -6. Let's see if I can squeeze a little graph in here so we can actually see what we were dealing with, and then we'll complete this presentation. Okay, we've got our coordinate axes. This curve looks somewhat like this. Moves along, passes through the origin, continues along, makes a curve back, flattens out temporarily, comes on around, makes another pass through the origin. Actually, the orientation is as I have drawn it. It goes along this direction and comes along here, then here, then here, then here, and so on. Now, just to give you an idea, this position right here is when, in this position, is when t is equal to -1. And we see above our point of horizontal tangency is at 2, -6 when t is -1. That is that point right there, 2, -6. That happens when t is -1. Now, when t is 0, if we look above, that was a point of tangency for a horizontal tangent line when the t was equal to 0. And that point is at 0, -9, which is in fact the point that we have right here. And yes, there would be a horizontal tangent line there. And likewise, when t was equal to +1, okay, as we're moving on along, our t is increasing, then it says that we have a vertical tangent line at -2, -6, which is this point right here, and yes, that seems to fit. We would have our one horizontal tangent line here at the bottom. Okay, there's our horizontal tangent line, and we have our vertical tangent lines at t equal -1, and that would be this tangent line, and a vertical tangent line at t equal +1 that happens at -2, -6, and that would be a tangent line right here. So you see what we've done. This helps make a little sense of it. This is the end of the discussion and lecture on calculus and parametric equations. Good luck on your homework.